Hi Pradeep. Hi Pradeep, can you hear me? Hello. Hello, hello, hello. Fuck, did it get connected with my. It got connected with my this thing, but now if I disconnect it, it will fuck up. 1 minute, I'll try to change. Hello. Hello. Hey, can you guys hear me now? I hope this works. You guys can hear me now, right? Yeah. We have 7 viewers. Let me try to start. Hi Shibe. Hello. Is Badri a new one? Yes, we have Yash Mahata too. See, I will teach you guys how to eat fries without getting your hands dirty while coding. You can use a tissue to take fries. Fuck, it fallen down like this, and then simple. I just went to. Is there a lag? I hope not. Okay, that's nice. Damn, 18 viewers. That's a lot. So, what do we do? Please start from D. People, newbies that think D is difficult, let me start from D. As I always say, this is not blue, this is red. Damn, it's different now. I thought it should be blue, but then it's red because division 2 will be red, I guess, because it keeps running, right? Still, you guys can hope that I haven't solved the problems. And then I'm just entering now. Damn, 69 solves. That's because current testing is low. See, all problems are the same. All problems are the same. C or A. Oh, I have to share screen. Fuck. Sorry, guys, for not sharing screen. Yeah. So I'll show you people. Okay, I have opened this chicken jockey. I think there is some meme also regarding chicken jockey. I don't know if it is meme or not, but chicken jockey is a famous thing. Okay. So is my screen visible? Because all problems are almost same. So let's try D. Okay. It's difficult or not, it doesn't matter. Let's try D. Okay. Newbies, let's try D. Shibe, let's try D. So Steve made the foolish decision to mine at night. Okay, to mine at night. Minecraft one. And came across a monstrous creature, the chicken jockey. Maybe we have to say it in a nicer way. I don't know the meme. What is power N means? Chicken jockey, chicken jockey, chicken jockey. Is that what it is? Power N means chicken jockey, jockey, jockey. I don't know what it is. Okay, chicken jockey power N. A chicken jockey power N consists of N mobs stacked in order on top of each other. N mobs it seems, with mob 1 at the bottom and mob N at the top. Mob I initially has health HI. So we have some thing called a chicken jockey. which has n mobs. Mob 1 at the bottom, mob n at the top, and each of them has health HI. Okay. In one attack, Steve can deal 1 damage to any mob. Okay. If any mob reaches health 0 or less health, it dies. And all the mobs on top of it fall down. Damn. And form a new stack. Okay. When you kill one, everything else will fall down and then form a new stack, it seems. The bottom mob of the new stack takes 1 fall damage for every mob it was on top of before falling. Okay. So the bottom mob will take 1 fall damage for every mob it was on top. So what is every mob it was on top? The below things, right? So for everything below it will take a damage, it seems. For everything below this mob of the new stack, bottom mob of the new stack will take 1 fall damage for everything below it. Okay. That is okay. They are explaining it again in a nicer way. They make some statements complex and then they'll explain the number of mobs below it in the previous stack, including the one that just died. Yeah, that makes sense. It got disappeared, but then now from this much height we are falling. This might kill it as well. Damn. In which case, all the mobs on top of it fall down again and the process repeats. So if you kill one, they all may fall down, and then because of that, this may die. But from here onwards, everything will fall only once. That's the statement. It looks like it's a repeating process, but then from here, everything can only fall once. Okay, because only the bottom one is taking the fall damage. Not everything is taking the fall damage. Okay, the bottom. That's why they have kept it in black. See, a question may be much more difficult, but then giving it a try doesn't need some great things out of your mind. Giving it a try just needs some fries to move forward. For example, consider Chicken Jocks is 6 with initial mob health 1, 2, 3. Steve damage is the third mob. Okay, now what happens? 3 will fall with tower damage 3 and then it will die. And then 5 will fall with tower damage 2. So it will become 4, 2. So what we have finally 1, 2, 4, 2. Yeah. So I think we have understood the problem. Well, Steve's watch durability is low, so he wishes to minimum attacks. See guys, minimization problems are obvious. They are solved already. They just want you to find some lower bound. Okay. Because if you prove that these are the minimum attacks required, you are also showing that you must do these many. You cannot do just min minus 1. It won't work. So we will find lower bounds, but still the problem may be much more easier too. So let's just this seems like a good problem, right? Because we have been given some array, we want to find minimum number of fall damages. So maybe if we make some one small observation, maybe the problem will be done. Maybe if we just try something, maybe the problem will be done. Okay. So let's try. What do we want? Minimum attacks. Okay. We can even try to look at the optimal. Let's say that we have killed this and then this and then this or like that. Okay. So how to work on problems? I hope I have viewers. I'm good, Padma. I hope you're good too. So I'll increase brightness so that you guys can see me clearly. So we want minimum attacks. Okay. To work on something, what can you do? Most basic idea. To work on something. Look at optimal or just something that you that you must do. Like, see what we must do. Let's say we have killed by hand. By hand means we have killed it by hand at some point. Some mobs. Okay, so we have one, two, three, up to so on n. Let's say I have killed few things. Let's say we have killed I1, I2 up to so on ik using our hand. Okay, this is the most basic idea one can work on. Trying to see the optimal or the whole thing so you can say some points and then you can use some logic. Maybe we can even try to think, okay, if, see, it is about finding necessary conditions. If this sequence of killing with hand is optimal, what can I say? Which is finding necessary conditions. And then if you find good enough necessary conditions, they may become sufficient. Okay, so the way we try to solve the problem is not out of the box. It's the same problem, right? It's the same problem. So let's look at this. Okay, if you are going to kill I1, I2 up to so on ik by hand, okay, killing ik first seems better as it takes most fall damage, right? Killing the last one first seems the, sorry, not ik, killing uh okay, this is not the sequence in which we kill. These are just some mobs we kill by hand. If we're going to kill all of them by hand, then killing ik seems the best, right? Because you're anyway going to kill it, right? So instead of killing once things get fallen down, kill it now so that above things will take highest fall damage. That makes sense, right? Huh? Take a moment to process. Damn. What else can we say? What else can we say? See, all problems are you want something. Then, okay, if this happens, what are the necessary conditions? And then they will become sufficient. Is my internet good? Nice, that's good to hear. So, uh, where are we? So then it seems the best thing, right? Now we can also say everything above ik for j greater than ik dies after you kill after you kill ik, right? This is so hot. Not me doing this shit, but the sauce is hot. Right. So what does this mean? Aj plus 1. For simplicity, let's okay. A of ik plus 1 less than or equals to ik plus 1. Why? After you kill a of a of ik plus 1 will take ik plus 1 fall damage, right? It will take that much fall damage and then it dies. Because why? Because you are not going to kill it by hand, so it gets killed by fall, right? And then a of ik plus 2 should be less than or equals to 1. Why? Because that's how much it's going to fall, right? Right in understanding the problem, because once it kills, it dies, and then 5 is taking only 1 damage. So we're right in understanding the problem because only the bottom one is going to take damage. But then this solves the problem already. I don't get it. Now it seems like trying to remove the first one. After you kill it, things will fall. Seems like a good one, but maybe not. Right. If you know what's the last one that you're gonna kill, then the problem is done because you will repeat the same. But what if there is no such a thing? Because you kill it, what's the cost? See, what can we say about last one? Ik. Once you kill it, above things die automatically. This you will say. Right. But then if let's just look at such IKs, okay, because this is a necessary condition, but it's not sufficient. So let's look at such IKs. You kill it, above things will die. Maybe for this also you kill it, above things will die. Can you find what's the best one among these? Maybe not. But then, if you kill it, what's the answer of the remaining things? It's just answer of remaining things, right? So let's call answer of remaining things as when you kill ik, answer of I. If it was my contest, I would have named it DP of I, but then you guys will piss your pants if I call DP of I. That's why I'm just writing it as answer of I. Okay. So we have answer of I. Seems less scary, right? Than DP of I. Answer of I is from 1 to I. What's the minimum cost? Because, so now, can we brute force all of them? Is a thing you can try on. Right. Can you brute force all of them? Is a thing. Right. We can probably. So seems the problem is being done. Do you guys get it? Hey Pradeep, KR, we are using logic here. Suppose if this has worked, what can we say is what we are trying to do? Okay, suppose if this has worked. Suppose if this has worked, then A of ik plus 1 will be less than or equals to ik plus 1. Okay, suppose if this has worked. What if A of ik plus 1 greater than ik plus 1? is your question. But that doesn't make any sense. We are just trying to use logic that suppose if you are going to kill these things and be successful, then if then this happens, okay? I'm not telling you random things that a of ik plus 1 less than or equals to ik plus 1. We are just trying to logically see what are the necessary conditions here, okay? Damn, suddenly all of a sudden these are empty now. I have Sprite, but then I don't like Sprite. I prefer water. I prefer water. So, is that clear, Pradeep KR? Is that clear? Let's try to brute force. Explain everything again, Shibe. I'll do that for you because you have asked me, I'll do that. So, we have a problem, right? Where we kill something. So, let's say that we have to work on something, right? Because we have to work on the problem. We cannot do random things. So what's the basic way to work on the whole problem? Like rather than trying to see, okay, what happens if you remove this, what happens if you remove this, let's just take our freedom because math logically we can write anything, right? So let's say suppose that these are the things, looking at the optimal or looking at this something that works or looking at the optimal itself is always good. It's always good. Looking at the optimal is always good because you have to prove the problem finally. So looking at the optimal is good. That's how we solve most of the problems. So I1 less than I2 less than up to so on ik. Let's say you these are the vertices you're going to kill by hand. Everything else gets killed by fall damage. So now what happens if you kill these things by hand? Killing ik seems the greediest thing you can do, right? Because once you kill ik first, the above thing is going to take highest fall damage right now. But then if something else gets killed, the above things will take only lesser damage. So killing ik seems the first. So how do we kill? We kill something and then we kill something below and then we kill something below and then we kill something below and then now we want what's the optimal value, right? So let's try to see what's the necessary conditions. Like if ik after killing ik, everything below it must die. Everything above it must die. For that to happen, we want for I greater than or equals to ik plus 1, ai less than or equals to 1. These are the necessary conditions, okay? For what? Once you kill ik, everything above it must die. For that, these are the necessary conditions. And now if we can find, so this is necessary conditions, but with this thing satisfying, there can be multiple IKs, right? There can be multiple possible IKs. So now we are trying to see if we can brute force on them or not. We are trying to see if we can brute force on them because these are the conditions, and then we are trying to see if we can brute force on them. Okay. And let's say if you fix some IK, among those things, if you fix some IK, among what such things, once you kill IK, everything will above will die. Let's call them as last possible IKs. First possible. So once you remove them, everything else dies. I'm sorry for going slow, but then it's fine, I think. So how do you find these things? So not how do we find, let's say clearly answer equals to answer of n equals to answer of ik plus sorry a of ik because you're killing it by hand, and then ik belongs to first possible, let's say, plus answer of ik minus 1, right? We have to kill everything. This is a possible thing. Minimum of ik, let me write like this. Ik, kill ik, everything about dice. See, people, if you guys don't know set representation, this is how we represent set. A set has one opening flavor bracket, one ending flavor bracket, some conditions here, and then all possible things that satisfy that condition here. Okay, so this is it for answer of n. But then answer of n is being dependent on answer of something less than n, which means if you find answer of 0, answer of 1, up to so on everything, then you're done. Right, then you're done. Then the problem is done. So let's try to see if this solution works or not. What all we did, we just found a necessary condition that killing the top thing is best. That's what we have done so far. And just using that, we can solve the problem in using this solution. Using this solution, we can solve, because we'll first find answer of 1, and then we'll find answer of top to so on, we'll find answer of n, and then we'll return that answer of n. Right? So int n, seen and int. See, my videos are beginner friendly, right? Because I'm a beginner. My videos are beginner friendly. I don't have any templates. I don't have segmentaries coming in between, right? So what is answer of 0? Probably it is, what's answer of 0? Probably it is a of 0, right? Only one thing is there, just kill it. It can't fall. Okay, answer of I, let's initialize to some value. Let's initialize to kill that thing and then kill everything below. Just initializing, because ik can be I, as there's nothing above I. See, when we say answer of I, that means only 1 to I exists, nothing else above existing, because here after you kill a of ik, what is existing? Ik minus 1 things are existing, above things are not there. So what does answer of ik minus 1 means? What does answer of I means? When you have only 1 to I, when you have only 1 to I, when you have only 1 to I, answer of I is minimum needed. Okay, so now what do? We will brute force. Okay, we will brute force, because everything above should be 1, right? So let's brute force. So let's try to see for int ik equals to I, or I equals to 0, I less than or equals to ik equals to 0, ik less than ik plus plus. Let's brute force everything. Okay, now what is the condition? Bool good equals to true, let's say. If first means you can remove it first. If a of ik plus 1 greater than ik, sorry, after it falls it should die, then first equals to false, right? And also what should happen? If j equals to ik plus 1, j less than n, j plus plus, a of j equals to, if a of j greater than, sorry, 1, first equals to false. These are the conditions, right? These are the conditions. And then if first, then, so if you remove this, everything above will die. Answer of I equals to minimum of answer of I comma a of ik plus answer of ik minus 1. But what if ik is 0? We have to trying to code. See, it hasn't. But then why will we have such a big value? This seems wrong, right? J less than I, right? Only till I exists here. Less than or equals to I. What is this number that keeps coming? Again, I just take this. So let me output all answers, okay? So that we can know what's going wrong or where it's going wrong. But then let's see it clearly once. What could have been wrong here? I have 25. I hope it's fine. So let's try to see this thing. What could I be doing wrong? Answer of n minus 1. Thanks, people. Answer of n minus 1. Okay. Answer of n minus 1. That seems wrong, but still it seems better than the previous value. Okay. So for this, the answer seems we are returning 2. Why are we returning 2? Ik can be 0, right? And then why are we returning 2 here? Why are we returning 2? Let me output these things. From 1 itself it says 2. Why? Can't ik be 0? This is just killing the topmost thing, okay? And then we are trying to see if we can kill below things. And then when ik is 0, we have, okay, 1 based index. Indices are 1 based, right? So this should be ik plus 1. I got confused with zero based index and one based indexing, right? That's why I wrote a answer of n. I got confused with one based indexing, so this should be greater than 1. Because if ik is zero based index, number of things below it, including it, or ik plus 1, right? Not ik. So if it is above that, fall damage is not enough. We have this seem to be working. There is some other error too. Let me just check once. Let me just check once. Are we missing something here? So let's just look at the answer of this one. We are telling it's 8, but then if you kill 4 and then if you kill 3, you're done. Kill 4, these things will fall. 1, 2, 3. Sorry. So it seems we are making a mistake. Okay. Somehow we are making a mistake. Fine. Fine. I have my WhatsApp open. Bro, show screen. It's just 2 minutes, people. It's just 2 minutes. I'm seeing WhatsApp. Okay. Okay, 5 minutes. Should I eat the sauce? Nah, I think. No. So let's see this. We are making some mistake. Maybe in understanding the question, then we are fucked. Let's try to see this example, okay? If I have made a mistake in understanding the problem, then we are really fucked. So, what does this thing say? Once, guys, killing the last thing isn't always good. Maybe killing, guys, everything is wrong. Everything is, maybe killing the last thing is not always good. Maybe. Right. If I have just seen this test case, I would have realized that. Still, it's fine. Still, it's fine. Let's see. Because why? What's the fault in our argument? What's the fault in your argument? Maybe killing AIK after it falls may cost lesser sometimes. Right. This is the only logical flaw that we made. Okay, that's why we are getting answer 9, answer 8, answer 30 using our force approach because it's wrong. So we have to be careful. Let's just see it again. It seemed right, but then may cost lesser sometimes. Right? It may cost lesser sometimes. So there are two cases now. If you going to kill this later, so right, if it doesn't take fall damage, then our previous argument is true. Right? If it is never going to take any fall damage, then our previous argument is true. Right? Is this statement clear, people? I want to go slow. I know, Tanjay, it's a simple DP, but let me try to solve it slowly now. So, so if it takes fall damage, then our previous argument is true. If it doesn't take any fall damage, let's say this thing you're killing it, but then it is never taking any fall damage. That means killing it now is best, right? But then if it takes fall damage, right? So maybe instead of brute forcing, let's see here. Let's see here a little bit more. Because I minus 1 comma I are almost always attached, right? So maybe we can write a simpler DP. So let's just, it doesn't take any fall damage at all. That means kill it. Okay. But then if it takes some fall damage, it will either be taking when you kill I minus 1. When you kill I minus 1, it will take fall damage, or when it will take fall damage only when I minus 1 gets killed by fall or hand. Right. I don't know why I assumed the problem to be this simple previously, but then it has some more, which is, see, you guys can see why how this comes logically. All of this comes logically. I mean, or if you observe a little bit also it comes, but then what I mean is to say removing that first is wrong. What's the problem? Because you can remove it, you can kill it maybe after it has fallen some. Then if you kill it, maybe you will reduce the cost, right? Maybe you'll reduce the cost, right? But then you can, okay. So now let's say we are killing AIK after it takes fall damage. Or or I know I'm complicating things again, but this seems enough. Maybe we can write something between I minus 1 comma I itself. Okay. Let's just look at the last one. Let's just look at last one. N maybe. Okay. If N gets killed by hand, if N never took any fall damage, then answer is A of N plus A of N minus 1. Answer of N minus 1, right? If it takes some fall damage, then then killing before thing seems good, but then maybe killing before thing, if it takes some fall damage, when I minus 1 is gone, it will take 1 or more, right? I know I'm again still complexing. I should have just done in my way. Not done in my way, I should have just at least tried solving the problem instead of getting stuck like this. Let me think for some time, okay? Please be there, let me think for some time. I mean, we can write two-dimensional DPs. I mean, we can write n squared DPs easily, but fuck, I can't solve this problem. Let me read E2. Okay, let's not waste the stream. Let me read E2. As a child, Steve yearned for the minds. His mind can be represented as a tree of n nodes. This seems interesting problem. This seems 5 by 4 n, right? So let's read this problem. This seems interesting. His mind. Let's read this problem to people. Let's not waste time, okay? Unfortunately, Steve's mind has been infiltrated by his greatest nemesis, Herobrine. At any moment, Herobrine is hiding in exactly one node. Steve's mind. Unfortunately, Steve's mind has been infiltrated by. See, we have to be very careful while making statements, right? I have thought removing IK is the best one by assuming something, but then that was not. But then that was not. I mean, the problem will not become too complicated. Why? After you kill it, it's not that complicated still somehow. But let's see. For AN itself, we can say some things, right? For AN itself, we can say some things that if it never took any fall damage, then kill it right now. Or so you will kill it by hand or you will kill it by fall. Okay, let's say that. If you are killing it by hand, then A of N, killing it right now is good. Instead of taking fall damage, yeah. If you can just kill it now. Okay. If it got killed by hand and some fall damage, then if you have killed n minus 1 by hand, then the fall damage may vary because you might have killed n minus 1 when it is somewhere, then the fall damage may vary. Else, the fall damage is 1. So, you can always, instead of doing this, you can always go for this too. Once it fallen a bit, then only you will kill it. You can always do that. So, instead of killing something entirely, you can always do something like this. Right? But still, let me read E2. Also, you people read E. It seems like a good problem with 5 by 4 times n. Okay. Steve's mind has been infiltrated by his greatest nemesis, Herobrine. At any moment, Herobrine is hiding in exactly one node. Okay. Initially, he may be in any of them, so he's hiding somewhere. Steve can perform the following operations. 1x. Check if Herobrine is currently in node X. If he is, Steve catches him. Otherwise, Herobrine may or may not move to any adjacent node except the one you just checked. So if he is there in that node, he is getting caught. If he is not there, then except this, he can go to any adjacent node, it seems, or he can stay in the same place, it seems. Okay. And then we have another operation. Destroy all edges connected to X. Herobrine can no longer be able to use them. Afterwards, Herobrine may or may not move to any adjacent node. See, this is a good problem. Doesn't involve any topics. It's just some constructive problem. It's a good problem. Let's try to use some logic and then solve this. And then I'll go back to D. I will surely solve D. Okay. Let's try this for 5-10 minutes and then go back to D. See, we have a proof that under the constraints it's always possible. So let's try to think of this problem. It's a nice problem. Okay. So E seems nice so far. So we have two operations. One, check in X, and then you win if he is in X. Else, he moved to adjacent except the one we checked. Okay. We have two operations. I can think of the problem too a bit. I unnecessarily wrote too much. I should not have. I wanted to explain it in a simpler way, but then we should find him in at most 5 by 4 n operations, regardless of where he is now. Seems a nice problem, right? So where he is initially and what he does, we can find him in. So this seems a nice problem. What is 5 by 4 n? It's just n plus n by 4, right? It seems a bit nice. It seems a bit of a nice problem. So we have to use this too. He can move to except. Once you remove that, he can move to other adjacent things, but he cannot come to this. That's another thing. So we have a tree. We have a tree. See guys, this seems a nice problem. So let's try it for some more time. We have a tree. Okay. And once you choose an X, if he is there here, he is caught. Else, if he is here, he cannot come here, but he will come here. This makes him to stay in the same subtree with respect to this, right? At least for now. Because otherwise, if he can come here, maybe he'll go here, we cannot say anything, right? Even if we take two things, he is here, let's say. Even if you take three things, let's say he is among one of these things. Once you take this, he may be here or here, right? And once you take this, he may be here or here. Once you take this, let's say he is here and then he moved here, and then you take this, he can again come back, and then you take this, he can again come back. So I don't know much about that one, but we have to use that too. What I mean is, we have to use this except to a bit, but then we have this power too. We can destroy everything, all the edges connected to that too. So we can even destroy all the edges too. But then once you destroy, I think we should we know where in which of these things he is right now? What information do we have? Let's say you are killing one thing. Let's say you have checked at few places, and then you're killing something. What's the information you have? Let's try this for some time. It won't be that difficult. We have to find a way. That's it. In 5 by 4 operations, which seems to be n plus n by 4 or so. What happens when you destroy something? Let's say after something you have destroyed this. Now we have many other components, right? And see, we can always check a leaf and then remove a leaf, right? That we can always do. But then we should be able to do this too. Even if it was a graph, this can be done 2n. But then we want n plus n by 4. That means we have to eliminate few vertices. Floor, right, or sill? What is it? Floor. So that means if n is 2, if n is 4, in 5 operations we can do this. So this statement is true, right? We can eliminate few vertices. So this problem says one thing for sure. If there is a tree, you can eliminate everything in 5 by 4 n operations. That statement is true for this. But once you remove it, if you are not sure if it can be here or not, so this seems it takes two operations, right? Before you remove x, if you are not sure that it cannot be here, then you must check later. Or, yeah, then you must check later. You must check it for sure. So just for that one node removal from possibilities, we have used two things, which means we should be knowing before removing some x itself that it cannot be here. N plus n by 4. Let's think for some more time. Just some more time. We can even try to do things like looking at a line graph or such things, like just a line or such things, but still, let me try to think for some time. We can solve this problem. Let me try to think for some time. See this thing. So, with this idea itself, with this statement itself, looking at four things may help us solve the problem, right? But then I don't want to look at that. This itself, see, if you remove X, if you know he's not here, you can surely do that. For the first X you're going to remove if you know that he is not there. So after some operations, we should reach a point where we can know that, okay, he's definitely not here. And how would we know that? By this fact that he can only move slowly. Using this fact, we will know that he's definitely not here, okay? He can only move slowly. Using this, we will get to know that he's definitely not here, and then we try to do such things like this. Let's look at four things for once, okay? Let's look at some simple four things. How can you solve this problem in five operations at max? Maybe do this twice, then you have one, two, three, done. Okay, that seems reasonable. But then let's say you have this. For n equals to 1, you can always just do in one operation. Right. You can just check that. But then for bigger trees, a bit bigger trees, what can we do? For n equals to 2 itself, what can we do? We can just check it's n plus n by 4, right? 5n by 4 is like almost n plus n by 4. Can we group four things and then just eliminate them somehow? N plus n by 4, right? Maybe if you can group four things and then eliminate them, even that may give us the answer. So let's look at this. Okay. It could have been anywhere now among all these three. Then we can check here. Now we have the two things. You can check here, you can check here, and then it's done. Right? How many operations we took? Remove this, and then we have to check that too. Two operations, three, four, five. Or if you look at touching everything once as separate, you have taken four things plus What is this thing? Do you have viewers? So guys, it's like we can touch everything once to check if it's there or not, but then we have to eliminate at least four things we have to eliminate, okay? So let's just look at this thing, okay? Guys, see these things a bit clearly. Let's look at just some four layers maybe in a tree where we need four vertices. From this leaf, let's try to collect some four vertices, okay? If we have like these four things, then we can just remove these four things using five operations, right? I can check here and then remove this. Check, check, check. How many did we do? Five. If we have something like this, we can proceed further. What does this mean? If any node has five operations, I mean, if any node has more than three leaves, we can proceed further. Right. If any node has more than three leaves, we can proceed further. Let's see what's next. Try to follow E, okay? If you are still here. The fuck you mean masters or CM are not sitting in your stream? So if some node has three leaves, we can proceed further. Which means we have things like this, not more than this, because then we can proceed further. Right? If you look at one thing like this, they have at max two things. That's it. Okay? At max two things. Okay? Like in a big tree, we are trying to see the some bottom leaves. If something has three leaves, we can proceed further. Because we have removed four things using five operations, and then we will solve the remaining tree, like induction. So now we have to worry when things are like this. Because here, if you follow the same idea, so let's say this has some other things too, okay? Let's say we have something like this, okay? Now if we can eliminate, see, for this, we can again eliminate these four things using five operations. I think so. How? Let's touch this thing first. Okay? Let's check this thing and then touch this thing. Two operations. Checked it, touched it. Now, you have these three things, but they are a line. They are just a line. Okay? Because they are a line, touch this, touch this, touch this. When you're touching this, you can only be here or here. And then touch this. You can only be here or here. And then touch this. So now again you have eliminated four things using five operations. Seems we have solved the problem. Will I get more views if I stream without having a shirt? We have no female viewers anyway, right? What spelling? So even in this case, we are able to remove. So now the only case that's left is anyone following other than Tunje? So we have eliminated this structure. Which structure? 1, 2, 3, 4. So greater than or equals to 4 leaves, we have eliminated. Something having greater than or equals to 4 leaves, we have eliminated. How? We can touch that thing twice. And then you can touch all these things 1, 1, 1. So it will be 5 by 4 operations at most. And then remaining trees you will again solve inductively. And then we are trying to see this thing. Let's say something had only lesser leaves. Okay? It had lesser leaves. If it had lesser leaves, let's say this is the bottommost thing. Okay, this is the bottommost thing. If this is the bottommost thing, if you go above, it cannot have further. If you see the bottommost thing, it cannot have a bigger tree, because then that would be the bottom, right? So we can always find this structure, or we can always find this structure for the bottommost leaf. If you take the bottommost leaf, its parent can have either one more leaf. If it is having another two more leaves, we are done. If it can either have one more leaf, or see, I'm using logic again. If I go to the bottommost leaf, I need not worry about these things having more, right? So bottommost leaf parent having greater than or equals to 3 leaves, we are done. Bottommost leaves parent having 2 leaves, we are done. Again, bottommost leaf parent having only 1 leaf. This is the only problem we have, right? Now what can we do? We need 4 things here again. It can be like this. If it is like this, you can just do this twice and then go over line. Because going over line helps us using the fact that he cannot move fast. If you have a line, you can go over each of them, check each of them in O of n. You can save a lot. Okay. So let's try to make solution simpler too. So this is the, if you can eliminate the remaining cases where the bottommost leaf has no other child and then like this, then we are done. But then if there is no other, we can see these two things as the same thing. Okay. But then you will check from that direction. Check that so that you can eliminate. So, but it's still not clear. Let's try to think a bit clearly. This has nothing. So these two are like a leaf, right? These two are together like a leaf. And how are we checking one leaf so far? Here we remove this and then check from one direction, right? These two are like a leaf. What happens? We'll check that direction and then it will be solved. Here, again we are checking only one leaf. We can check one leaf from one direction. See, you can check one leaf in O of 1. Sorry, in one operation. You can check these line in n operations. This line of n thing can be just checked in n operations. Check here, check here, check here, check here. This is the fact that we are trying to use. We are trying to use line things a lot because line just needs O of n. We're trying to use this as our base, right? So here we can try to look at, so we're trying to see induction again. For we can simplify the process after getting a clear, perfect, proven solution. But then until then, maybe we have to go a bit deeper. So until then, I'm trying to go a bit deeper in using induction. That here, all we have is single leaves. Single leaves can be extended to this thing. So I'm trying to compress 2 leaves into 1 leaf, but they can be extended again because here we have only single leaves. Here we have this thing, but then that is not a single leaf. These two are like leaves. So these two things are acting like a leaf. So it would have been just here, and then we can come from one direction again. Okay. So what are we trying? If you can touch something twice and then everything left is just these paths, then we are good. That's what we want. Let's say you have like this and then this. So we are trying to see this case, right? This is the bottommost leaf. This thing doesn't have anything. Let's say if this thing also doesn't have anything, then we can touch this twice and then we had a leaf. We have a tree of 4 things, we are done. So touch something twice. And form line graphs of size greater than or equals to 3, then you are good. Now we can just do 5 operations and eliminate 4 things. Okay. So let's try to see, these 2 things are clear. Let's try to see this thing a bit more case wise. Here I have tried using induction to just solve using these 2 things itself, but then let's do something case wise too. If we do something case wise, again here, this thing can have something. If it doesn't have, touch this thing, you are done already because you form 3 line graph, you iterate over that line graph easily. Okay. If it has something, it cannot have multiple things, let's say, because if it has multiple things, let's say we have already removed that. If it has something, there will only be one thing, right? Still, after this also you can just touch this and then you form line graphs. Line graphs, you can eliminate them by just going over all of them. So the problem is done, very clearly done. If this has multiple things, okay, if this has multiple things, you will first choose that, let's say. But if that doesn't have multiple things, if it is not even existing, touch this, you have a line graph. If it exists, touch this, you have again some other line graphs. If there is one more thing, touch it, you again have line graphs. But then if it has more things, you can still touch it. Then you will solve this later again. If its size is greater than or equals to 4, you're good. If the size is greater than or equals to 4, wait a minute, you touch it twice, but then you cannot touch it twice again here. So let's make sure that this is simple already. Okay, let's just make sure that this already doesn't have more than three things. Okay, let's just make sure that. If you make sure that, then what happens? Then we have three cases here, one, two, three. Here you can just touch this. If this doesn't have anything, if this has something, and then that also has something, you cannot have two because that thing has already been eliminated. Then touch this, you're done. Okay, touch this twice, you're done. But if this is also not there, again touch this twice, you're done. If this is also not there, touch this twice, you're done. Because now we can go over this in a line graph. Bro, I was explaining a lot using screen. Why can't someone text me? It's gone 3 minutes ago. I don't know why I'm not getting notifications. Okay, yeah, I heard texted. Sorry. But see, guys, what I was telling was, if you touch twice something and then you form line graphs, then we are good. Okay, because if you touch something twice and then you form line graphs of size greater than or equal to, then you have done something. You have eliminated four things using five things, right? Five operations. Because line graphs, you can just come from one direction and then they just take n operations. That's the main idea we are trying to force on this problem. Okay, just this is the only idea, that line graphs need only n operations. This is the only idea. Line graphs need n operations. That's the idea we're trying to force here. And then, so what's the solution? If something had three leaves, if the bottommost vertex, if the bottommost non-leaf had three leaves, we are done. If it is having only two leaves, even then we are done. We will touch the parent twice, we are done. Okay. Because we are forming a line graph. But then, if it is like this, and then its parent is there, If it parent has something, we are done. If it parent has two things also, we are done. But then if parent doesn't have anything and then it goes like this, then we have to touch this shit. And then we go over these three things together. If you touch this, maybe you cannot solve the problem properly. If you touch this thing twice. If it is like this, you have to touch this thing twice. You guys can see the screen, right? See, now we have to think of a simpler implementation, okay? Now we have to think of a simpler implementation. Let's look at from the bottommost leaf. Let's try to go above until we get a size 4, okay? From the bottommost leaf, let's try to go above until we get a size 4. If you're getting size 4 here, we are done. If you're not getting size 4, we will go one more step above, right? And then we are done. From the bottommost leaf, we have one more case, right? Where we have bottommost leaf, we have here, but then here we have something, right? In this case, first we have to eliminate these things more, okay? In this case, we have to eliminate these things more. From the bottommost leaf, try to go first time above 4, but this we have to eliminate first. If these things doesn't exist at all, means if you don't have, let me be clear. So, if you look at three vertices, they can only be like this. Three vertices are only line graphs, right? Three vertices are just line graphs. With three vertices, you cannot make anything except line graph. So now what will I do for implementation? I will try to find the bottommost vertex with size greater than or equals to 4. Bottommost vertex with size greater than or equals to 4. Everything below will be of size 3 at max. And with size 3, you cannot form anything better than a line graph. So see the implementation now. From below, find the minimum subtree of size greater than or equals to 4. Touch that shit twice. Everything below will only have less than or equals to 3. And then you can just touch all of them simply. Done. Simple solution. How is this? You people can't be helped. You people really cannot be helped. You guys get a chance to try some harder problems on your own. You guys get a chance to know better implementation techniques, better solving techniques. See how I have solved the problem. I have made many statements. Logical statements that made me approach the problem better. And then I have solved the problem with this shit, that this observation that line graphs are good. They help us remove the operations. And then I tried simplifying, and then I tried checking some inductive proof so that I can go forward with more confidence. And once I got more confidence, then I just simplified the implementation with this shit, that just go and find something with size greater than or equals to lowest thing with size greater than or equals to 4. Remove that twice, so I have done two operations. Everything else are line graphs. All of them will need just one operation, because with three things you cannot form something more than a line graph. With three things, all you have is a line graph. And for line graphs, you come from one direction. So implementation is simple now, right? So is implementation is simple. Proof is simple. only one observation about line graphs, that they need less operations. And the logical statements I made here, they don't need great ideas. If you guys see how we build something, you know why AI is dumb? It's not because it cannot make so many small logical statements and then go towards a direction, right? I have to make a video where grandmaster versus AI if I ever become grandmaster. Then that may get views. So before you remove X, if you are not sure, this is bad. So here I got to know that we must do something like that. We must do two operations. If you don't know that, if you are not sure, that that is not there, and that's what we are doing in our final solution too, that we have to do two operations on that. And then this observation I came a bit late, but then if you have this observation even before that, I have told, right? I have told we can even look at line graphs, but then I didn't. But then if we have just looked at line graphs, we can see these needs only n operations. And now try to use both of them. Now try to use both of them. So we want lowest thing with size 4. In this case, this would be the lowest thing with size 4, right? We want lowest thing with size 4 and then we remove that. And all the subtrees will be of size less than 4. So we have to keep finding lowest thing with size 4 and then remove that. How do we do that? So we need some nicer implementation because we can anyway do, maybe we can go to the lowest layers. We can do such things, right? We can always come from below. I want a simpler implementation. That's why I'm trying to say, think. So let's do it like DP, okay? So not DP, let's do it like recursively. We have from root. So what our DFS will do is, what our function will do is, it goes over all the subtrays, okay, of size greater than or equals to 4. If size greater than or equals to 4, it processes this thing, and then it will only leave, it processes all the smaller things, it removes all the smaller things, and then it will only leave something less than or equals to size 3. That's our assumption, let's say. So what will you do this? You will remove all the smaller things, and then finally the whatever the leftover thing is there, that will be left out of size less than or equals to 3. If you can do that, you're good. So what's our DFS should do? Remove things and then leave, remove things from below and then leave less than or equals to 3 things. This can be our DFS. So now we'll go on to some tree. If its size is less than or equals to 3, we can just leave it like that. If its size is greater than or equals to 4, we will see, we will process all of its subtrees. Okay? We'll process all of its subtrees. Size is greater than or equals to 4. We have this 1, and then we have these 3 things, right? But all of these also have been processed into things which are less than or equals to 3 things now. Their DFS will make sure that. Then you do this thing twice, then again do. Done. Simple recursion done. Do you guys see my implementation again, how I simplified it? So what I mean, take a uh, let's say this is what we want. Now what can we do? For DFS of V, if size is less than or equals to 3, do nothing. If size greater than or equals to 4, then you have V, and then you have other things. Now do everything. Okay, we do everything now. We do everything in the sense we do. See, we have to first process these things, because once you process these things, it may totally disappear, right? It may totally disappear. It may totally disappear, and then you have to check if the size of this thing is. I mean, we are trying to remove things from the below, right? So what I'm trying to do is I'm trying to do this thing recursively by trying to remove first for children's, and then try to see if this size is greater than or equals to V, and then if size greater than or equals to 4, and then apply. Okay. So we process this, make it less than or equals to 3. Process this, make it less than or equals to 3. Process this, make it less than or. I think we can just do the same thing. If the size is less than or equals to 3, do nothing, because it's already been into less than or equals to 3. If the size is greater than or equals to 4, you have at least 3 such things, right? So you process all of them, maybe they have been removed. So when you're processing it, you're just removing such things, right? So this is less than or equals to 3 now, this is less than or equals to 3 now, this is less than or equals to 3 now, this is also less than or equals to 3 now. But after doing all these things, if the size is again less, if the size is again less than 3, because only one may remain, right? Then again you should not apply this twice. You can just leave it like that. Okay. Even after doing this, has size less than or equals to 3, do nothing. Else do V twice, all its children are now of size less than or equals to 3, right? Do process them. So we can even make implementation simple by our DFS returns after processing children the line of the 3 things we have. So if it also returns this line, we can just traverse that line, right? If it also returns this line, then we can just traverse that line now. Do you guys see my implementations again? It seems complex now, Pradeep, but then we are just trying to remove we're just trying to remove lowest greater than or equals to 4 size. Okay, if you look at lowest greater than or equals to 4 size, what you can logically say is all its children will be of size less than or equals to 3. And then we can try to do this simple implementation too, but then I don't know why I'm complexing things. And then because I don't want to update subtract size, that's why I'm doing this. Maybe you can maintain them in some set and then maybe you can do this, but then so once you remove this twice, now you have at least three vertices, but all of them are line graphs. If all of them are line graphs, you can just traverse them in O of n, and then you have five operations for four things, so you're good. So this is what our idea is. But then what I'm trying to do is, because we are coming from down, I'm trying to use the same idea recursively. Okay, it's just recursively trying to remove four things. So after removing four things, what's the final thing left? Something less than or equals to 3 will be left, right? So we are assuming our DFS does this recursively. Okay, because we have to do below things first, we are trying to use recursion. Do you guys get me? We are doing the same thing, but then we are trying to use recursion to do that for us. What we are trying to do? Find the lowest greater than or equals to 3 things, remove that. We are trying to do this, but then we are trying to do it recursively because once you remove all of them, what's left? Something less than or equals to 3 is left in the top, right? So our DFS does this. Let's say. Now what should we do? Now, what should we do? First, we have to process all the below things, right? First, we have to come from down. That's why we have to process all the below things. And after processing all the below things, let's say all of them will become some whatever is left. We can maintain that as a list. Okay, it may be entirely gone. It may not have been entirely gone. Now, if the size is greater than or equals to 4, you can do this twice. And then everything else you can just traverse. So I made implementation even further simpler. I made implementation even further simpler. If you guys see now how easily I can code this vector int. So we have some line graphs, right? So this will give me the path is what I'm assuming. Okay. Whenever size is less than or equals to 3. Okay. I can just keep void and then even use something like this. So once you do DFS, it finds you the path, is what is our assumption, right? It finds you that path. Okay, so remove children, everything, remove from bot children's first, process child children first. What does DFS do? It removes everything and then it will return, and then it will store temp of v. We're clearing here, so temp of v the will have the final line graph that remains after you remove all greater than or equals to 4 things. Okay, this is our assumption. So you're trying to remove all the children's first, because we're coming from below, trying to remove all the below greater than or equals to 4 things. Now only a line removes, only a line will be there. But do you guys see how this has more logic and less of topics? So believe me when I say there are no topics. Okay, what topic does this use? Segment tree, persistent segment tree. I don't know where you guys learned all those things. Like, you guys try so hard to slow yourself. I really don't get that. Even now we don't have viewers for ye. Why? They think it's out of their reach. They slow themselves. People slow themselves. People fool themselves. People wanna tell comforting lies to themselves, like there exists heaven. I mean, I believe in God, but still. Uh, so DFS of, so it will find this tempo of V, right? So now what happened? It finds its tempo of V, and then those three things will remain. Those three things will still remain. Okay, we are not removing them yet. So now we have its children. Each of them can be of size whatever is remaining. Okay, so now let's find the size. So now we have this size 2, right? And below things are all small things. If size greater than or equals to 4, then what do we do? Answer the pushback of, I'll first break, okay, 2 comma V. I'm breaking it, and then I will check V. Okay, now below things are all of size less than or equals to 3, right? So what will I do? Below things are all size less than or equals to 3, right? I'll just go over those paths one after the other. Because they are less than or equals to 3 things. Done. Nothing remains here. Nothing remains. Everything is removed now. But if size is less than 3, then this thing remains. Here we should find the path, right? Here we should find the path. So, how many children can there be? Right? Only two children. If only one children, then so if the size is 3, how can it exist, right? If the size is 3, how can it exist? If the size is 3, it can either be like this from V, or it can either be like this from V, or it can be either be like this from V. That's it, right? And then we have to find this path, this path, this path. How do we do that? I mean, we can store those things, Pradeep, but then once we remove things, you have to again maintain them, right? So my solution is much simpler, right? Which is find lowest greater than or equals to 4 size, lowest greater than or equals to 4 size, and then it guarantees that everything below that is of size less than or equals to 3, and size less than or equals to 3 are just line graphs, and then you remove this twice, and then you traverse those line things. That's what I have done. Size greater than or equals to 4 things, do that twice, traverse those remaining line graphs. This is 2 plus n, making sure that remaining are at least 3. So it is 2 plus 3, 5 by 4. So we are good. Here I just want the path now. I'm just thinking how to get the path now. Okay. How to get the path? If it has two children, put one children this side, put V middle, and then put this children that side, right? So if I can make sure in my recursion, whenever it is like this, I will size less than 3 means these things, right? So whenever it is like this, I will start from top, and then I will maintain this 2 in temp. Whenever it is like this, I will maintain this in temp. Whenever it is like this, so I will just make sure that we come like this in temp. So now what can I do? If there are two children, if two children, then child 1 V, child 2. If there's only one children, then temp of V equals to V, comma, temp of child 1, because this will make sure that it goes, if it is this, it comes first and then it comes first next, so that we will have, that's it. Or we can come from below so that we can just add, or if I make sure that it comes like this, then I can just add this to the end. So I'll just do that. Instead of this, I'll just do, this is just simple shitty thing. We can do this as we like. We can even brute force things. We can do it as we like. It's just trying to find that path. It's just trying to find this or this as a line so that we can process them simpler here. Okay. We need not even process them now. We can even process them later. We can even process them later. We can even actually process them later. Like when you do this, make sure that this has been removed. And then finally, everything else existing are line graphs now. Then you go to that line graph, find one end, and then you traverse them. But instead of that, I am doing everything even more recursively because I can. Okay. So now we could have had those things here itself. Int vector int child's child's dot pushback of u. Well, they just don't have p. That's it. So it cannot be 3. We're trying to come from below. When there is only one, below or above is same. So now we are done. We have removed everything below and then we finally found whatever the 3 length path that's left for V. First we have removed everything for children's, whatever is left. If V itself can be removed, finally nothing is left, nothing is left. If something is left, whatever that left, we are trying to make them as a line. So now what should I do? For int V, temp of 1, now whatever is remaining, I have to add them also to answer, right? But then this problem is very direct. The fact that it can be solved for some smaller things itself says to find something so that we can progress further. Let's see how it works. Okay. I mean, I'm just doing 1, comma 1. And then, why am I not traversing this? This is the right one, right? What happened to my brightness suddenly? So now we are doing right. Why 2 came before? Because I wanted to push V after this. That's why we're coming from down. That's why 2 came first and then 1 came. If you see, if you look at this, the problem is obvious from the fact that if you see n equals to 4, you can do that in 5 operations. Because see n equals to 4, n equals to 4, you must do that in 5 operations. That itself solves the problem very directly. Now all you have to do is find some below 4 things so that you remove those things and then you can repeat. So it's very direct problem. The fact that n equals to 4, I have told that too. That if you see n equals to 4, we can solve it easily. So it's an obvious direct problem if you're not scared and if you can use some logic. So that's why I don't think it's that good of, I mean, it's good problem still because you have to use some logic, but it's not too difficult, right? The implementation I complicated, maybe you guys can do simpler implementation. So now if you see this, we have only removing one ones, okay? 1 2 2 3 2 4, right? So we are removing one twice and then everything else will be a path, and the path was 2 3 2 4. So 3 to 4 was the path. 3 to 4 was the path. Let's submit this. It is asserting, guys. But why? Do you have viewers? See, every time you use one more operation, you're removing at least 4 things, right? Every time I'm living on you, you don't make it easy, no, no. Wish I could be there for you. Give me a reason to. Every time I'm walking on, I can make you turn around. Falling for myself, but you won't back down. Even if you got to get on right now. I know you're scared of the unknown. So, every time you push something to answer, right? Every time you push something to answer, you're removing 4 vertices at least. When you're pushing 5 things. So that should work well. It should not assert. Is it assertion fail? Let me check implementation one more time. First remove from childs. Find the size after removing childs, whatever the smaller things remained. If those things will make up to greater than or equals to 4 things, then you can first remove this, traverse all the paths. I'm clearing everything before using. Let me just remove assert. What's wrong, guys? Did anyone find an answer? How? Is my solution wrong? So, x things, right? X greater than or equals to 3. I hope this is not wrong. I hope implementation is wrong. X plus 2, x operations plus 2 operations. Is it less than or equals to 5 by 4 of x plus 1? What is x? Children, this is 1. X greater than or equals to 3. So x plus 2, because I'm doing x operations here, 2 operations here. This is my logic, right? So if you see that, for this to happen, what we need? 4x plus 8 greater than or equals to 5x plus 1. And this is also true that 5 by 4 of n1 plus n2 up to so on is less than or equals to, is greater than or equals to. Is splitting them a good idea? You're removing them, and then is this true or false? Is this true or false? It's true, right? This is also true. I'm just checking this thing again. Like removing something, is that good? Because this is true. Together they may give more value, right? Here some reminders are lost. Too many reminders are lost. So I've done everything good, but still why am I not able to solve this shit? Wait. Okay. But maybe it's wrong. Solving this thing. See, it should be right. Solution is right. Right. It could have been empty. Yeah. See, the fact that there is a child doesn't mean there is temp, right? The fact that there is a child doesn't mean there is temp. They may not exist sometimes. They may not exist, right? Or I can do like this. Yeah, this works. There can be any other error. My eyes are hurting. I slept a lot in the afternoon. This is wrong again. Why? Let's see this case. So, one temp comes from below. And then, wait, it's true. It's right only. It's right only. I was thinking maybe we are not forming the path properly, but then the path is less than or equals to three things, right? So it can only be, it can be this. Okay, here it's wrong. If the path is this, we add this first, we add this first, and then we add this. Childs may be two. Childs may be two. Childs may be two. But then what do we need? So implementation has a major flaw. These are not, you're not concerned about childs. You're concerned about active temps. Okay. So let's add those things. So I'll remove whatever the childs that array we have before. We want active childs, right? If that's not empty, these are the childs we're trying to look at now. Right. So the original childs doesn't matter. After you remove everything, whatever is remaining, those childs we want to see. So whatever remaining, these childs we have to see. Every time I'm walking on, I can hear you, I can hear you, I can hear you. Turn around, run from myself and you won't back down. Even if I gotta risk it all right now. I know you're scared of the unknown. This won't have any error. I don't like Sprite, but let me drink Sprite. So, is this problem out of your reach? It's not out of your reach, bro. If I have solved it, you should be able to solve. I was struggling on D, right? Okay, it was hard. I agree it was hard. But is it not doable with a bit more time? See, you have to see the structure from the above. The fact that you can solve for all n, if you can remove something. See, bro, it's not graphs, bro. It's not graphs, nah. Okay, maybe you can say that, but then this is not okay. Maybe you are telling that because of my implementation. But then it was line that mattered more. See, it's logic. I'm using logic to say this statement. But it's even see what I use more because I use more points even before. See, if I had made the observation before, it would have been easier, right? But then I have to solve even difficult problems, right? Not just this problem. I should be able to solve even difficult problems, right? So what do? I make some times I make things complex because even if it's not required to solve the problem, it's my way of solving to go in steps. So this one I have done. See, this we can say before you remove X, if you're not sure that he's not there, then you have to check it again. That's costing you a lot. That's costing you two operations. That's costing you a lot. So we should not remove much. And line paths we need not remove at all. So it's not even the fact that he moves slowly. If it's a line graph, he can only move in one direction and we can catch him without using 2 at all. This is the simple fact they are trying to use. See, try to look where we need 2 operations. Here we need 2 operations, but then in line graph, we don't need 2 operations at all. Line graphs, we can do n. If you look the problem from above, the structure, everything, if you look from above, sometimes we have at some place we have to save operations. Here operations are must. If you're trying to do something like this, you must do that. But then you should have a place where you can do you can get the freedom. It's 5n by 4. 5n by 4 is n plus n by 4. Per if you do per n, it's 5 by 4. But per n you cannot take 2. But you must take 2. That means at some place there is a lot of freedom here. At some place there is a lot of freedom, and the freedom comes from line graphs. And even if you try to look at n equals to 4, you can say this thing. N equals to 4, the problem demands you to solve in 5 operations. This also gives us ideas. So if you guys are not scared and try to do what you can do, then you will do all of these things. If you try to do what you can do, but then you will think you are not strong in graphs or such things. Okay, this is not graphs. So let me try C. I will solve A and B2. I will solve A and B2. Let me try to solve C. And then I'll draw A and B. Okay. Be fresh again. I have to sleep too, but let's get fresh again. Let's try to read the problem. D I have already tried, so I won't try it again. It's failed. I'm not able to solve it, let's say. Having recently discovered the nether, Steve has built a network of n nether portals at each different location in this world. Each portal is connected in one direction, so to number each portal is connected in one direction to some number of other portals. Damn. Oh, I'm doing that a lot these days, hitting myself to the desk. Each portal is connected in one direction I'll try to be a bit quick. Steve refuses to tell you which portals are connected to which. To avoid getting lost, Steve has carefully built the network of portals so that there is no sequence of jumps through portals that will bring you back from the location back to its formally directed acyclic graph. So we have directions we won't come back. It seems Steve refuses to tell you which portals are connected. So it means there are no cycles. It's some directed graphs. Graphs are simple, guys. Graphs cannot get too complicated. Is this water? Steve refuses to tell you which portals are connected to which. No, it's not water. I don't like 7 Up, but then this seems okay. But he will allow you to ask queries. So we don't know what are the edges here, what are the allowed traversals, like from where to where we can go, we don't know. But then he allow you, see, graph is simple. You can go from here to here, but you cannot do that for everything. That's what graph is, right? Directed graph. And then it also says there are no cycles back. In each query, you give Steve a set of locations and a starting location X. Steve will figure out the longest path starting at X that only passes through locations in X. What is this? You have some vertices, you have an X, and what he will give you? The longest path starting at X that only passes through locations in X, S, and tell you number of locations in it. Steve will figure out the longest path starting at X that only passes through locations in S. Okay, so that's what we get. So it cannot, from X, you cannot take anything else. You have to only use these things. And then whatever is the longest path is what you get. Okay, maybe we have a lot of freedom here. Maybe we don't have much freedom. Let's try to see what we want. Are you looking to obtain the achievement hot tourist destinations? You want to find any path that visits as many locations as possible. What do we need to find? So there is some longest path, and then we have to find that path is the question. We have to find a path that starts somewhere, and then that will be the longest. Damn. If you understand the problem, we can only do two inquiries. It seems. Okay, we can only do two inquiries, and we should able to find a longest path. So what does the problem say? We have a graph, we don't know it, we can do such things, but then we should be able to finally find the longest path possible. We should be able to find that. Any such longest path, okay? We can do two inquiries. So using two inquiries, we should be able to find the longest path, because if there is a path that is very long, see, in the path, all of them can appear only once. Why? Why? And once do we find, what should we do? We have to find that path, and then we have to output that path too. Sorry, output that path too. Output that path too. Damn. Output that path too. It's difficult. Path, put, teeth are coming soon after, like a tongue twister. This denotes starting portal V1 and then jumping to V2 and then ending at VK. So we have to find that longest path too of maximum length. We are given this, we should be able to find that path itself. We only have two inquiries. Seems like we have to do some magic, but then let's see. Let's see. What can we do? Okay. Can we find the length of the longest path from here? I think it's done. I already got it a little bit, but then yeah, let me try to go logically so that you people don't think I'm able to solve it quicker. Okay. So we have to prove to that this is the longest path, right? Can I get the value? From here, what's the longest path? Can I get that value? That's the first question. Simple thing we can think of. Can I can I get the longest path possible from some vertex V? Value of the longest path. Let's try to have such a thing because you have to finally prove to that this is the longest path, right? But can we have such a thing? From some vertex, can I know what's the longest path possible? Can I have such a thing? Guys, anyone has not solved the problem, I will try to go slower for them in the live. Has anyone not solved the problem? See, yeah, John J, I know it's easier than you think, but then I can solve it. If I reattempt it, I can solve it. I know that. Thanks for that. Sir, इसमें B is just sorting, you'll solve in seconds. Fine, but don't spoil the problem to me. Sir, इसमें greedy काम नहीं करेगा क्या? बीच में? See, approach for interactive problems, Pradeep, cool. You want C, right? It's not that, see, you have to see the problems from a general sense. Interactive problems have some nicer things in them, but still you have to use logic, okay? So, see, if you believe that proofs are simple, implementations are simple, like if you believe that proofs are simple, that directly gives out that having something like this is useful. That what's the longest path from this vertex? Having this is useful. Can you get this thing? Uh, Whoever has not solved, Samyak and Pradeep, cool. Can you get what's the length of longest path for some vertex way? How would you get that? Yeah, Dyson's theorem, we can just do K1n, right? K1 to n. I hope you, 1 to n, that's what you meant. So, with this, we can know the longest path from V. Did you get offended, Gamer Lord? See, Samyak and Gamer Lord, you guys have to read the problem. I think you guys haven't read the problem. The problem is C. In the problem C, we are not given edges, but then we are thing that we can do. Given a starting vertex x and instead of vertices, you will get the longest path from x to there. Okay, that's what you get. So now, using this, using question mark v1 2 up to so on n, we can get the value of longest path from v for all vertices. Let's do this for all vertices in n operations. Now, can we find the path in n operations? So, we know what's the first thing can be. Take some vertex. Okay. Now, so we have vertices of longest path. Let's rank those vertices. Longest path, we have some vertices v1, v2, up to so on, right? And then we have longest path -1. Even here we have some other vertices. Some other vertices. V5, V6, and so on. So now we want to derive that path itself, right? Can we find from one vertex v1? Let's say v1 is one vertex, right? Can I find the path from this? What should I do? If I know from here to any of this there is an edge, then if I can just find that one vertex that has an edge from this, then I can do the same thing repeatedly. See, in all the problems, we do things repeatedly. When you guys are given two n operations, it was just two types of operations. One type is to find the longest path, the other type is to find the path. To find from v1 whatever is there to this. So now to find the path, I'm trying to start with some longest vertex. We have to start somewhere, right? Start with some longest vertex and then try to see from here to here if there is an edge to this or not. You are going to touch everything at most once again because you are going in this direction, right? You will touch this once and then you will touch this one, all of them at most once, and then you will touch next things at most once. From there you will try to find from here to here if there is an edge or not. Okay. So can I find if there is an edge from between this and this in one operation? What will I do? v1 comma v4. So question mark v1 comma v4 will tell me so what will I do? Uh, I will I won't sort them. Okay. Sorting increases complexity, right? So I won't sort them. So what do? We want max distances, right? We need max distances. Let's just say, let's just maintain those vertices itself. Vector int. See, vector int, if you guys don't know, it is to group things as a list. Okay. I will try to make this list itself. Once I know the longest path, I will add that vertex to its longest path. Okay. Uh, let's just keep it v. Of paths can be of size 1 to 0 to n plus 1, right? So for this, what do we do? So now we know the longest path from I is x. I'm just pushing that vertex I into size v. Okay. So now I'll also may find the answer itself. Okay. Answer is just the max path that we find, right? So now, so now for so now we can just start with some vertex uh, x equals to so to find if there is an edge or not, you can just do v1 comma v4. And then if it's 1, there's no edge. If it's 2, there's an edge. So it's simple. You guys should not get scared. I think int s equals to starting vertex equals to v of answer of 0. Some vertex, any arbitrary one will work, of size max length, right? So now Let me do answer minus minus, or like, okay, now from I equals to answer minus 1, I greater than or equals to 0, we can come till 1. That's it, right? 1. We can just come till 1. We have this path S. We find answer minus 1 path. We find the next one. We find the next one. And then we just add that. So here we are. Now what do we do? We should find the vertex that that has an edge. So from S to V of I, if there's an something in V of I, T in V of I, if there's an edge, we can proceed further, right? So let me go over all the possible T. V of I. I is just answer minus 1, okay? And then it will be answer minus 2, answer minus 3, up to so on. And then we have to output C out question mark S if x equals to 2. Then s equals to T break. And this will definitely exist because if that path is actually answer, if there exists an actual path, that means there definitely exists an edge from here to here. And whose max path is that? Right? Its max path cannot be more, then the whole max will increase. Its max path cannot be less, then this itself would not exist. So this we can surely find. Because that path is there. So that should have been there. Right? Because it's the max path, it's like tightest. You cannot have that next thing before. You have to be careful logically here, okay? What if v4 is here, and then you have from v1 to v4 to up to so on? That cannot be possible because then you have v1 to v4 and then up to so on, which is even longer. So that, because it's longest, it's like tightest, you cannot do anything else. I'm just trying to explain a bit more to show the existence, because clarity is all the difference it causes for solving some much higher rated problem. Clarity is all that is needed. It's not like you have to get great ideas and all. If you are not being clear at every step, you will fail at higher problems. I mean, more difficult problems. After you know that s equals to 3, I'm breaking. So now I know the path, the next one. I can increase the path by one more by pushing this to that. And then we have the answer in 2n operations. Is this clear, people? Someone was asking me B. Let me quickly solve B. Okay. Fuck. Fuck. I was thinking a lot about that, but then I fucked up after that. We should read the problem carefully. Don't do like me. Okay. We have. I thought S is included by them, but then it's not. Here everything is included. Okay. I wish I knew you wanted me. What do you do? What you do? Made a move, could have made a move. Okay. Format has been fucked up here too. I bite my tongue, it's a bad habit. Got a mouth that I didn't take a stab at it. Thought you were too good for me, my dear. Never gave me. Let me try to read this. See, in Codeforces, they actually make them appear difficult. That you guys should be happy about that, because even this looks difficult. Even E looks equally difficult, right? E looks equally difficult. So unless you try, you cannot say what's an easy problem, what's a difficult problem. Do you guys get that? So you guys have to try everything. So let me read this problem. Steve lives in a village of n other villages. Unfortunately, due to disputes over the distribution of emeralds, none of the villages are friends with any other villager. Furthermore, village I initially has grumpiness GI. Okay? Steve can perform the following operation: any number of select two integers I and j, then give them max number of emeralds to share. Damn. The higher guy will be pissed off. Some communist ideas they are having here. Take both of their emeralds and then split them. What does grumpiness mean? Yeah, it sounds like what it means. And both of their grumpiness decreases by. Damn, and then they'll become friends. It seems. This seems a bit complex. Max emeralds and then min, and then you will just remove them. So it's like, okay, they will share them. Okay, to share, because they are friends. Because they are friends, they are together having that probably now. They are sharing them. They are having them together. Steve wishes to make every villager friends with each other. That is, from any villager, you can follow a path of friendships to reach any other villager. Since you do not want to inflate the village economy too much, calculate the minimum number of emeralds you must give away to accomplish this. Damn. We want minimum number of. See, we have to connect people. You have to connect everyone. You have to connect all the people. Because it's connecting people, we can say it's a tree, but then not worry about that. We have to touch everyone at least once, right? But then do you see, we will give maximum number of emeralds to share. So whenever you touch someone for the first time, you will at least you will at least whenever you touch someone for the first time, you will at least give them that many emeralds. So you must touch n minus 1 times, right? So it's like you will group two people. I think, see, when you touch someone, you will at least get that many. You will at least get that many, right? I think we can only avoid gn minus 1. If you do, let's say these are in increasing order. If we do gn and gn minus 1 together, for them being together, we can get gn number of animals. Oh, but then their grumpiness decreases too. Okay, I haven't thought about that. But still it holds. Still it holds. Still it holds. What holds? Whenever you touch it for the first time, if you are touching someone for the first time, then their grumpiness haven't been changed at all, but still you will use at least that much. So that means uh, if you are touching someone for the first time, we should connect everyone. So this shows that answer is sum of all the things. But but you can initially touch two things at a time. But after this, every time you touch something new, so the answer is at least this much. So we can ignore one thing now. And I'm telling, if you do g of n minus 1 comma g of n, then you can save g of n minus 1 and then it becomes 0. Now you can get uh, all from 1 to n minus 2 using this 0. Because it became 0, now we can take 1 comma n minus 1, you have your answer. 2 comma n minus 1, you have your answer. So you are trying to miss g of n minus 1. But think, if you can miss g of n, that's the max, right? You will have you will have at least this much. You can only ignore one. But think, if you can ignore the last one. You cannot. The first time you touch it, that's what will appear. There is no way you can ignore that. The first time you touch something with g of n, that will become 0, and from there you can take everything else. Okay. So ignoring g of n minus 1 is the best thing you can do. So what do we need here? We need second maximum. I want sort. Sort is O of n log n complexity. And we don't need n log n complexity here. We need second maximum. If n is 2, we can get second maximum. Okay. M, let m be the first maximum. Let both of them be minus 1 zeros initially. M2 be the second maximum. Okay. So we are traversing. We also need sum. We're traversing one by one. We got a new element. We will add it to our sum. And then we got a new one, right? If x equals to x greater than m, then our m2 becomes m and m becomes x, right? We are having two maximums. Now x came, this goes, these two will remain, and then this will become m2 will be m will be x. Else, if x equals to m, let's say if x less than m. Now if x greater than or equals to m2, so we have m2 here. If x falls here, first two maximums, if x falls here, then m can be, the maximum will become m, x, and then m2 will become m. But if x falls here, then second maximum will get updated. But if x falls below, it doesn't affect at all. Simple cases. And now what's the answer? Sum minus m2. Someone gave me this is about sorting, but then it was not. At least to me. I'm just joking. Did I made a mistake? We should look at samples sometimes. Here we are able to remove this 6, 7, 8. But then they had a lesser score. Fuck. I made some mistake somewhere. Sorry. Sorry for all of this. Oh, both of their grumpiness decreases by this much. Still, let me see this. So we have here 2. We have here 5. And then we have here 2. What the fuck? So my logic had flaw somewhere. Every time you touch something for the first time, what does this mean? Okay, one observation is once you make them zeros, you guys can see how I don't think at all. I'm not thinking at all, and then I thought like logically this works. I'm not even seeing anything in the question, but then I'm thinking this will work. But then it's wrong. Because okay, okay, I took these two things as true, but then you can touch things in n by 2 operations itself, right? You can touch things in n by 2 operations itself. I thought we have at least this many operations, and in every touch I thought we can only get one more. But then doing things together, not just once but multiple times is better, probably. Okay, so now we must sort. Sorry, now we must sort. So, see, because I thought this is n minus 1, I thought only 1 is missing. Do you guys see it's not just random? Like I use logic to solve problems. That if you see here, we can touch multiple times, right? So now we can do n by 2 operations itself. We can just pair them all well. And then every time you pair them, maximum will appear, right? And then minimum will become as if you have done that 0. And after these n by 2 things, you will have enough zeros and you just merge them. Do you guys see why I missed that? Why I missed that is because I thought at least these are needed. And so because of that, I thought at least we have to touch everything once. But then you can touch two things in n by 2 operations itself. So this is wrong. This will give greater than or equals to n by 2 things. N by 2 GIs must exist. N by 2 GIs must exist because you have to connect them all, right? Floor, seal. You have to connect them all, right? At least once. But after this, now let's think. After sorting, you cannot escape g of n again. But then you can escape g of n minus 1 by pairing those two. And then think, you cannot escape g of n minus 2 again. But then you can escape g of n minus 3 by pairing those two. So the answer is now done. Sorry for this solution because, but then you guys see how I'm using logic. It doesn't come from random. It comes from the observation that if you touch two things, I mean, because the problem is easy, many can get this easily, I guess. Maybe they randomly sort, maybe then they take them. Those are right. I haven't even thought of sorting right before doing. But maybe we'll sort and then try to experiment a bit, and then maybe you will come that okay, doing this may be seeming good. And if you see example 2, we have zeros combining. This I missed, right? Logically, I have missed that. It's time 142. The fuck you expect me to do everything right? I'll sleep, guys. Sleep is important. I have work tomorrow. Let me solve A and then I'll sleep. Send that money to me. Whatever you're sending to that guy, send that money to me if you're seeing my stream. I'll buy some Sprite. I prefer water. Sprite doesn't seem that bad though. Steve stumbled upon a collection of N-gears where Gerai has teeth. Yeah, he wants to arrange them in a row. After he arranges, Steve will spin the leftmost gear at a speed of 1 revolution per second. For each of the other gears, let x be the number of teeth it has, y be the number of teeth it has to the left, z be the number of z be the speed of the gear to its left. Then the speed will become y. It is z. It is x, right? And number of gears will have to match. I don't know, but then this, I think angular velocity is same. Let's think of that. But the number of their angular velocity is same, right? In general, so angular velocity itself was given, and then not angular velocity is same. Their contact speed should be same. The contact speed should be same, right? If the contact speed is same, more number of games. I mean, I'm just verifying the formula, but okay. Steve considers the contraction satisfactory if the rightmost gear spins at 1 revolution per second. Damn, this is spinning at 1. He wants finally to also 1. What does this mean? They have to all cancel out, right? They all should cancel out somehow. 1 times this by this into 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 this by this. All of them got cancelled. Which means if the first value and the last value is equal, then you can do this. See, 5, 5 are equal, you can do this. So it's like writing them down, everything cancel. If first and last number of grids are equal, then you can do this. Else you can't do this. These are not integers, these are like real numbers. So if there are two things, then you can do that. Else, no. Because the values are small, let's solve this easily. So I'll take an array of. Guys, we have to do easy problems too because people are paying courses. Isn't that stupid? I mean, if I launch a course, then it's not stupid, obviously, because mine is premium content. But because mine, you cannot get from love over like the way I solve, right? See, 286 solves, and we are one of them. See that? I can read F, but not D. But then let me try D. Okay. Hi Vedant Pandey, how you doing? Yes, Mohata. Yes, Yash Mohata, you have told me that. But then I got confused with the n minus one. If you can see that, right? Let's go to F. You mean, right? Good night, Samyak. I'm not in quant, bro. Not in quant. Yash Mahota, thanks for staying all the time, for listening E too. Okay. I mean, because you were listening E, that's why. I think others also have listened E, but then thanks everyone for just staying. Bye, I'm leaving. Good night. Thanks. Try to sleep properly. I'm just working at Apple, bro, but where are you, like, company? Currently, I'm at work, working at Apple, but maybe I have to see. Bye, Tanjay. I cannot solve D. Sorry.